doing? Ready for the weekend?
Mm-hmm. So ready.
Well, before you're going to have to work on your homework, okay? If you are very efficient today, you might finish the homework today, which is due next week. So as a reminder, you have a homework due tonight. I hope you already finished that and submitted the homework. Mohammed is going to grade it during the weekend. No, maybe, I don't know, next week. But we'll try to get your grades as soon as possible to you, okay? Okay, so I just want to say a few more things about horizontal stress, and then we'll talk about the homework. The first thing is that when I was taking a look at this plot in my office, I noticed that the direction of my wellbore was not really parallel to the direction of SH mean. So I really meant here that to have these stresses in the same direction as that stress over there, okay? And if that's the case, then your fractures are going to be all planes like this, and this is going to be the opening direction. So, you know, you could also do a wellbore here in this direction from the top and do multi-stage fracturing starting at those points. What will be wrong with that?
Fracture will grow along the well.
We'll grow along the well and we'll connect with the others, and we'll eventually link up into just one huge fracture. But the area of that fracture in contact with the reservoir is going to be much less this one than that one. The objective of having fractures which are separate to each other is to increase the surface area in contact with the reservoir. You should imagine this as a tree, right? This will be the branch of the tree, and this will be the leaves of the tree. You have leaves in a tree because they try to maximize the surface area to get more sun and more carbon dioxide too, so to capture that. And in this case, it's the same. We're trying to maximize surface area, and in this case, you do not maximize surface area. We talked about calculation of vertical stress, and this is what we're going to see today in the homework. But how would you go in measuring or calculating the horizontal stress? So we said that for SV, we can apply this formula, and we'll get SV. What about SH max and SH mean? How would you determine those?
Poisson's ratio.
How?
Poisson's ratio.
Poisson's ratio. If you have taken production, did you guys take production already?
Taking right now.
Taking it right now? Okay, towards the end of the semester, Dr. Bomer is also going to go through the production aspects of hydraulic fractures. And in there you will see that you could use Poisson's ratio in order to calculate horizontal stress, but that assumes many things. And we're going to see that next week. And we're going to use the same equations, but we're going to take it one step further into a more accurate calculation of effective stress, and also to consider what are called tectonic stress. Well, the short answer is that we do not know what these stresses are. And you could use the Poisson ratio some simplified method in order to calculate it, but still you don't know. You don't know how close you are to the actual value. The only way to know SH mean, assuming that this is the minimum principal stress, would be actually to conduct some sort of hydraulic fracture test. And we're not going to see the specifics right now about how we will do that, because we're going to do that later on. But I hope that you see by now that in order to open these fractures, the minimum pressure necessary in order to do that has to be at least the minimum principal horizontal stress. It's the same as blowing a balloon. The minimum pressure to blow the balloon would be the pressure outside the balloon, and in case of the balloon, also you have to overcome the elasticity of the balloon, right? And in this case, it's going to be similar. The minimum pressure necessary is going to be the minimum principal stress. So if you do a hydraulic fracture test in which you measure pressure, that's going to give you an idea about what is the minimum principal stress. And also we're going to see later on, in order to determine SH max, which is actually more difficult to determine, you can use measurements of wellbore failure in order to determine what that value is. But SH max and SH mean are going to be pretty difficult to determine, not as easy as SV. And that's why SV always is going to be your best friend, and it's going to be the one that is going to be the easiest to determine, and always the first step to solve in any problem that we're going to do. And that's what we're going to do now in the home. Yes?
From the fracture test, if we can figure out what SH min is with how much it can open, can't we figure out SH max with how far the fracture property is?
No, it's not gonna, SH max is not gonna impact much that. What it's gonna impact how far it goes, it will depend your injection rates, mainly, and the properties of the rock. But SH max is not going to play a significant role. Okay, so let's go to work on the homework, and homework is starts with a simple problem. So we're going into problem 2.4, and the first one is to compute the vertical stress gradient resulting from a rock which is 70% dolomite and 30% calcite, and it's filled with brine. Wait a minute, I thought I had provided a link for the density. So you may start writing down that 20% dolomite, 30% calcite, 10% porosity with this brine, okay? I'll give you 2 minutes, and then I'll put that link that you can go on your phone on it, and then you will find these values for the density. If you have any questions, again, just let me know. Mohammed is here to help you. Okay. Remember that all of this is online, so you can access it on your phone. Let me look for that link. Okay, here it is. This is the link, okay? And there you have second column is density. Okay, so now you have everything you need. Now you just have to do some unit conversion, and you will get the answer. Yes. As a reminder, 1 gram per cubic centimeter is equal to 1,000 kilograms per meter cube. All right, so let me know if you have any question, okay? Or if you want to tell me a story about your weekend, anything. I'll be going around. Yes. Oh, the table is messed up. That's for the porosity. So, the table is messed up.
Wait, do you know what the porosity is for? Yeah, so you have to use it, like, so you have to do this. So you have to go from trying to be bulk. That's the equation for B bulk, and you have the density of the fluid, and then you have to find the density of the matrix, and then that's when you use this. Yeah. Thanks. No problem, babe. I just have a problem with the unit conversions. I hate unit conversions. I'm just gonna get them all into grams per centimeter, then I'm just gonna convert it at the end. It's 1,000. 1,000.
What are the units?
No, I'm just asking you. I just didn't know. I'm just asking you to write down.
Both need one minus the at least that's how I think it is. I think it's right.
All right, guys. Let me say something here. I see that some people are going slightly different ways, but the solution should be one. It's always the same. Here, there is a very similar problem in which instead of the density, the mass density of the rock here, you should use the average of combining, the volume average combining calcite and dolomite, right? So what was it, 30% dolomite or 30% calcite?
30% calcite.
So then you should do 0.3 times density of calcite plus 0.7 density of dolomite. That will give you the density of the matrix of the mineral, and you get the bulk, and then you multiply the bulk times G, and that's going to give you the gradient. I'm asking you just for the gradient, okay? Pay attention to the units. I strongly recommend that you work this out in metric units, and then you convert those to field units. All right? Yeah.
Did you get 25,000?
I got 32,000. What did you get for the bulk density?
My book was 3.8. Grams percentage? Grams percentage? Yep. Did you get no, I'm converting it. Just 1,000. For the grams percentage.